Hi everyone and welcome to the next lesson on this topic. Today we are looking at the periodic table and its development. As with all of the lessons so far, it'd be really useful if you had a pen, a piece of paper to write on, and also for this, if you had a copy of the periodic table, it might come really useful at some points. Our challenge today is to be able to describe how the periodic table is arranged and how this changed over time. Our aspire is to be able to explain how the periodic table links to atomic structure. So let's start with a little task. I've put some cards on the screen. Each card has a colour and a number, and I want you to have a little bit of a think of how could we group and arrange these cards. Now, one of the ways you might have thought of is to group them all into groups of colour. Now, then they would look like this. However, that doesn't really take into account the numbers on the cards. You might have also thought to put the cards into number order. Now here, I've placed them in increasing number order and in rows of 4. But as you can see, when I get to 12, 14 and 15 wouldn't match with their colours. So you may have thought to have combined those two methods and placed them in columns of colour, but each column to be put in increasing number order. Now, the task I've just given you is a little bit similar to how the early scientists were looking at the periodic table. And if they were looking at periodic table, the number they had would have been the atomic weight, as they called it at the time. We now call it atomic mass, but then it was referred to as atomic weight. We all know that mass and weight are different things, but they weren't that sure on that at the moment. And the colour would have represented properties, similar properties of the different elements. So do they react violently with water? Are they toxic coloured gases? And that's why we did this activity. So we're going to look at how through time that periodic table has developed. So, like I've just said, early scientists were in a similar position to what you were then. And they wanted to find an order to the elements because as scientists like to think, everything has to be in order. They knew very little about the elements compared to what we know now. And actually, they weren't working with a complete set of cards, so to speak. Not all of the elements had even been discovered. So when they were trying to find order to what they knew of the elements, there were several that weren't even discovered, and had they been discovered, it would have disrupted their work. So we're going to look at the work of 3 scientists. The first scientist we are going to look at is Dobereiner. Now, Johann Wolfgang Dobereiner put the elements into what he called triads, groups of 3 that had similar properties. So he said, I think groups of elements with similar properties come in 3s and I will call them triads. Now you might notice that he has also placed them in increasing atomic weight in each of those triads. A little bit to how we did that last set of the coloured numbers that I gave you. Now then we got another scientist, and that is Newland. Now Newland was actually a musician, he was a keen piano player, and he went with a different law, which was the law of octaves. And he said if you order the elements by their atomic weight, then every 8 elements you would get a similar property. And that was a little bit like the second time when we put them in rows of 4 and then increase the mass, and sometimes it didn't quite fit with our properties. So that was Newland's octaves. Now then we have our third scientist. So we've got Mendeleev. Now Mendeleev ordered the elements again in order of their atomic weight. So all 3 scientists here have used increasing atomic weight. But here, I also grouped them in columns of elements who have similar properties. And I left gaps and made predictions about undiscovered elements. When people discovered the elements, they believed me. So the fundamental difference with Mendeleev's periodic table is that he was taking into account that actually we may not know all of these elements yet, but that also led to some people not acknowledging his work. Now, if you look at Dobrina's triads alongside Mendeleev's periodic table, they do fit quite well with each other. So the 3s did fit. So if we look at lithium, sodium and potassium, they would be in the same group on Mendeleev's periodic table, but Mendeleev just had a few extra elements in there. It wasn't necessarily 3, but we are still grouping in terms of properties as well. Now what I'd like you to do is I'd like you to summarise the method that was used by each of those scientists. So let's just go through the work of each of those scientists. First of all, we've got Dobrina. He had triads, and the triads, the 3s, all had similar properties. Then we got Newland's. Newland's had all of his elements going in order of increasing atomic weight and in a row of 7, and then he'd start the next row and continue with increasing weight. Mendeleev again used increasing atomic weight. He grouped the elements with similar properties, and sometimes he would swap them round to make sure they stayed in that group with the similar properties. And he also left gaps to account for any unknown elements, and he predicted the properties of those elements. Now Mendeleev was the closest. Mendeleev didn't simply leave it at this periodic table. He predicted the properties of some of those undiscovered elements. The issue was that his work wasn't really recognised, as he couldn't explain the presence of those gaps. He didn't have evidence for them, and he wasn't quite as respected as some of the other chemists at the time. So I'm going to play a little video on Mendeleev. I really like it. It explains his work really, really well.
The periodic table is instantly recognizable. It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius, up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitri Mendeleev, is a bona fide Science Hall of Famer. But why? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really, that had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their two-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitri was making a bold statement. He said, and I'm paraphrasing here, "Y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum. Eka being Sanskrit for one. Nobody's found Eka aluminum yet, so we don't know anything about it, right? Wrong. Based on where it's located, I can tell you all about it. First of all, an atom of Eka aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh 6 grams. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behaved. A few years after this prediction, a French guy named Paul-Émile Lecoq de Bois-Baudran discovered a new element in ore samples and named it gallium after Gaul, the historical name for France. Gallium is one step away from aluminum on the periodic table. It's Eka aluminum. So were Mendeleev's predictions right? Gallium's atomic weight is 69.72. A cubic centimeter of it weighs 5.9 grams. It's a solid metal at room temperature, but it melts at a paltry 30 degrees Celsius, 85 degrees Fahrenheit. It melts in your mouth and in your hand. Not only did Mendeleev completely nail gallium, he predicted other elements that were unknown at the time: scandium, germanium, rhenium. The element he called Eka-manganese is now called technetium. Technetium is so rare it couldn't be isolated until it was synthesized in a cyclotron in 1937, almost 70 years after Dmitri predicted its existence, 30 years after he died. Dmitri died without a Nobel Prize in 1907, but he wound up receiving a much more exclusive honor. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named Mendeleevium in 1963. There have been well over 800 Nobel Prize winners, but only 15 scientists have an element named after them. So the next time you stare at a periodic table, whether it's on the wall of a university classroom or on a $5 coffee mug, Dmitri Mendeleev, the architect of the periodic table, will be staring back.
So now, our periodic table is essentially Mendeleev's with the gaps completed, and we've added other groups like group 0, which were discovered much later on. We have groups which are vertical columns going down, and there are periods. The group tells you the number of electrons in the outer shell, and the period tells you how many shells. Don't forget hydrogen and helium to include that in your periods. That is the first period. Now I'm going to play you a video of me annotating a periodic table, just to point out some key features. Hi everyone, this is the periodic table of elements, and this is the particular one that you would receive in an exam. Now what I'm going to do in this video is I'm just going to annotate this with some really key features that would help you in using it. So the first key feature is the key in the middle. Now the key tells us what every single number and symbol represents on this table. Now in that you can see that we've got the atomic proton number, which is the bottom number on each element, and it is the lower number. Then we've got the atomic mass. Now the proton number is the number of protons, and the relative atomic mass is the mass of the nucleus, so it is the number of protons added to the number of neutrons. If we look at the periodic table, we can see that there are some patterns to its arrangement. So the first thing is that it is arranged in order of increasing atomic number, which means every time we go across, the element gains one proton. So arranged, this is the first way it's arranged, increasing atomic number. The second way it is arranged is to do with the groups. Now the groups are the columns in the periodic table. And what the groups represent is the number of electrons in the outer shell of that element. So every element in group 1 will have 1 electron in its outer shell. Every element in group 4 will have 4 electrons in its outer shell. The next thing we need to know about is the periods. Now the periods represents the number of shells that each element has. So if we looked at helium, helium's got 2 electrons and only 1 shell because it's in the first period. Neon has got 10 electrons, 2 in the first shell, and then 8 in the second shell because it's in the second period. Argon has got 18 electrons, 2, then 8, then another 8. So dependent on an element's location in that periodic table, we can find out pretty quickly how many electrons that element has and how they are arranged. So if I just pick one at random now, beryllium. Beryllium is 2 rows down, so there are 2 shells, and it's in group 2. So the second shell will have 2 electrons. So beryllium would have 2 electrons, then another 2. Now, there are a few other things we need to know when we are using our periodic table. And the first thing is a quick way to figure out where our metals and our non-metals are. So if we find aluminium and we draw like a staircase going around aluminium all the way down to the bottom of that periodic table, typically anything on the left of that would be metal, and anything on the right of that would be a non-metal. there are just a couple of specific groups that we need to know about now. So group 1 is our alkali metals. Group 2 is the alkali earth metals. This middle block is the transition metals. Group 7 is the halogens. And group 0 is the noble gases. Remember that group 0 is unreactive because it has a full outer electron shell. So there we go. That's our annotated periodic table. So now I'd like you to describe how the periodic table is arranged in terms of, first of all, protons, and then how it's arranged in terms of electrons. So in terms of protons, the periodic table is arranged in order of increasing number of protons. And in terms of electrons, all of the elements in each group have the same number of electrons in their outer shell, and each period has the same number of electron shells. So now it's time to have a go at an exam question on this. So we're just going to read through these first three first of all, and then I'll give you some time, and then there's a longer question on the next slide. So figure 1 shows an outline of the modern periodic table. So we've got figure 1, which is blank, and then there's some letters throughout. J, L, M, Q and R represent elements in that periodic table. So they want you to tell them which of those elements has 4 electrons in its outer shell, which 2 elements are in the same period, and which element has 3 electron shells. So now we have a longer answer question to complete. So the first thing we're going to do is we are going to bug the question. So first of all, we've been asked to evaluate, which means we need to summarise the advantages and disadvantages and use that to justify a conclusion. So let's have a look at what we are evaluating. So in the 1860s, scientists were trying to organise the elements. Figure 2 shows the table published by John Newland in 1865. The elements are arranged in order of their atomic weights. Figure 3 shows the periodic table published by Mendeleev in 1869. Mendeleev's table became accepted by other scientists, whereas Newland's table was not. So they want you to evaluate Newland's and Mendeleev's tables, and they want you to include a comparison of the tables and reasons why Mendeleev's table was more acceptable. And they want you to use the two figures that you have been given. So what you may wish to do is look at the groups of each of those figures to see if there's anything that stands out. Okay, so mark scheme for the first bit. Our first was J, then M and Q were in the same period, and L had 3 electron shells. The next bit is for our evaluation. Now remember, we're all aiming for a level 3, and for a level 3 it's a judgment, so we need to say which one's better, strongly linked, and logically supported by a sufficient range of correct reasons. The range of correct reasons that you could have is here. So we've got comparative points. Both of them have got more than one element in a box at times. Both of them have similar elements in the same column. Both are missing the noble gases, and they were both arranged in order of atomic weight. Then we've got advantages of Mendeleev or disadvantages of Newlands. Newlands didn't leave any gaps to account for any undiscovered elements, or Mendeleev did. Newlands had many more dissimilar elements in columns. In fact, some of the columns had metals and non-metals in them. Mendeleev left gaps, and sometimes Mendeleev changed the order of some of the elements to make sure